right, moving on. Now we're going to be doing the worst case runtime. Okay, so we consider the following algorithm. Okay, so we take a look at this. So first of all, we get inputted some type of a list, and if the item I, and you should pause the video for a second to take a look at this because I already have, obviously. So okay, so we have two loops here, and I usually just write it out like this so I can clearly see the difference. And then just quickly I will take a look. I will go like, okay, well, worst case this runs n, and then the worst case here, I'm gonna guess it runs n squared. Okay, so let's take a look at this. So we want to find a good asymptotic upper bound on the worst case. Okay, so usually when they ask us this, I like to do this because it's easy to think about. So here, okay, not the best drawing, but this really helps to understand what exactly you're looking for. So let's, okay, so, and then we have two lines in the middle. Okay, so this would be the best case omega, best case O, worst case omega, worst case big O. Okay, so let's think about what they want from us here. They want a asymptotic upper bound on the worst case, so they're looking for this. Now since this, you can kind of remember that this is the straight line. This is the largest runtime possible by statically analyzing the code. Okay, so then we go, so let's start writing it here. So for loop 1, we know that, okay, rather for loop 1 we let everything inside the loop be considered a single step. Then when we look at the code, we know that, you know, for I in range, we know that for I in range would be start at 0, it would go 1, 2, and it would end at n minus 1. So if we consider this first a single step, then at most this loop runs n times, so n steps. Okay, and then we consider loop 2. Okay, so each time it iterates, and then count 1 could increase by 1, which means in the worst case, this count becomes the length of n, right? Okay, so when we're considering loop, actually we want to consider the inside loop first, so then we go, okay, loop 3, okay, and then we go let j, rather we fix, oops, okay, see here, we fix j, and consider each step in loop 3 to be a single step. Alright. And then we know it's k in range, so loop 3 runs j times. Okay. Let me just scroll down a little bit here. Perfect. Now we need to consider loop loop 2. Consider loop 2, and then we say, okay, so at most count is equal to n. So loop 2 runs n times, assuming everything inside counts as a single step. Okay, and then, oops, way too down. Okay, so we have these two loops, right? So loop 2 runs, okay, and we know that it starts at 0 and it goes to n, and we know that it runs each time it goes into the third loop here, j amount of times, so j. And then notice here we're given this equation, so that's equal to equal to, oops, okay, equal to n plus 1, 2. Okay, so the code in worst case runs in n plus 1, 2 plus, and then we have from loop 1 n, which is, and we have 2 powers of n here, and then we have n, so which is in the big O of n squared. And that's it. Okay, so we want to describe a family, an input family whose runtime matches the upper bound that we proved in 1, and that we proved in part A. So what we want is, erase this here. So what we want here is we want this to iterate every time this happens. This means that, okay, well, count starts at 0. So count starts at 0, so we can, okay, first of all, we let n, okay, and then we say let L be a family of inputs size n, so it's an arbitrary size n such that, and then we can say, since our input is going to be L, we say L 0 equals 0. Okay, that means that this will be true the first time. And let's see here, so each time we want it to iterate, so we can say L1 equals L0 plus 1, right? It's kind of like recursive in a way. And we put dot 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 L, and then this will run to, it's a, for I in range in Python, so this will run to n minus 1. So this will be the last thing here, equals to L1 before the last one, L minus 2 plus 1. So each time count is, AI is going to equal count. So yeah, that's all we have to do for this question. We don't need to analyze. Okay, so now we want to find the best runtime. So we take a look at this. Okay, so prove the best runtime. Okay, so we want to be, okay, so this is what we want, the best case. So best case be the, okay, so best case running time, and we want the big O. So this is best case omega, best case O. So because these dots mean that we want a family of inputs. So we want to find a family of inputs such that it runs in n times. So we take a look at the code again. Okay, so how can we make this run in n time? That means that, well, make it run in n time. That means that this loops no matter what, right? But count is equal to 0, so this one never does. So this runs in n, and that's it. There's no n squared. Alright, so we need something that always will be false. In other words, the AI will always be smaller than count. Well, that's easy, so let n be a number, and then, oh, okay, wait, we assume that n is larger than 0, so, wait, okay, actually, we can say it's a natural number and put a little plus there. And then we let L be a family of inputs, size n such that, okay, so we say every number in L is equal to -1. So if that's the case, then, you know, this count remains 0 and this never happens. So since we know, okay, so then we do the same thing again as before. So we say loop 1, let all inside be one step. Then loop 1 runs in n steps. Perfect. And then since, take a look at this again. So in the test I would rip these papers apart so I can look at it at the same time. AI equal to count is always false. Count remains 0. So loop 2, loop 3 never runs. Thus, big O of n. And that's it.